Yeah, welcome to the 9th lecture in Introduction to Lattice Boltzmann in winter semester 25-26. Now we are in 26. Today is Epiphania, the day when the houses get blessed in Germany. We are moving house, so I hope that the next house will also be blessed. It's not a holiday for us, so we have to work, and this takes us back to the Lattice Boltzmann methods today with multiple relaxation times. Again, we have a lot to cover today, so let's see whether we can get everything into this 2 hours. So we have to talk about efficiency. Efficiency is a big problem for computational fluid dynamics because computational fluid dynamics requires a lot of degrees of freedom to work properly, and this means there is a lot of cost involved in doing computational fluid dynamics. So the question is always how to minimize the cost of CFD. So this is, of course, a problem that Lattice Boltzmann has this in the same way as other methods have them. So it's always a question how to make them as efficient as possible. And in order to investigate this, what we do is so-called performance modeling. Yeah. We can have entire lectures on performance modeling. We keep it pretty simple here. So we had it a little bit more in the other lecture, in parallel computing. So now specifically for the Lattice Boltzmann methods, we define the computational cost. We call it capital C now. And this will depend on some things like the domain size. The domain size, which we call V as in volume. So of course we talk, our domain is given as a volume, and we also have a duration of the problem that we want to simulate called D, and this is a time. So in general, we have a 4-dimensional problem. Yeah, because we have 3 spatial dimensions in one time. And then all of this, of course, depends also on the performance. Performance P. Now, the performance in the context of Lattice Boltzmann specifically is given in the units of node updates per second. And this you will often read in literature as NUPS, node updates per second. Or you can also read LUPS, lattice node updates per second. Yeah, sometimes you may even hear CUPS, cell updates per second. So this is a kind of a philosophy. Maybe we have already talked about this. There is an interpretation of lattices as lattice nodes, and this is compatible with how we did the asymptotic analysis as a collocation method, where we evaluate velocities at this point. And then there is a different interpretation often used by computer scientists who do not do the analysis, and they use cells instead of points, implying that they integrate over a cell. Yeah, to second order, this is actually the same. But usually analysis is always done in points and not in cells. This is why we always talk about points here, even though you will find literature where they talk about cells instead of points or nodes. So, what is performance? Performance is the number of lattice nodes times the number of time steps divided by the wall clock time of your simulation. Yeah. So you have a volume. This is a number of lattice nodes. Your volume translates into a number of lattice nodes, and your duration translates to a number of time steps. And now you have to you will run this simulation, and this will take some time, and this is then your performance. So, and the lattice nodes, of course, the number of lattice nodes, we call it n, is equal to the volume divided by the grid spacing cube, obviously, right? And the number of time steps is, okay, we call the number of time steps, we call it t, and we define this as the duration for our simulation divided by the time step. Yeah. So then the computational cost C can be written as the load that we have, namely n times t, and this divided by the performance. This is our cost. Yeah. Well, I mean, you can define cost in different way here. This is the more or less the cost in time. Yeah. You could also have a cost in memory. But this only matters when you're, I mean, usually this only matters whether it fits into your machine or it does not fit into your machine, right? Here, time is always an issue. So now this can be written as the volume times the duration, and these are problem-specific things, yeah, that you cannot, there's no, okay, they are problem specific, so you have a given problem, so they will be constant. You cannot manipulate them, yeah? So what you can manipulate is the performance by buying a better computer or employing a better software engineer, yeah? Or being more clever yourself, asking artificial intelligence, whatever you like, yeah? More performance. The other thing is, so here, delta x cubed. So if you make delta x smaller, then your cost will increase, right? And the same for delta t. Not exactly the same. I mean, one thing is you will often see people trying to improve, to increase performance by using a very small time step, but you should actually use a very small, very large time step. But the grid spacing has, of course, a larger impact because it goes in with the cube, obviously, yeah? Has, oops, a larger impact. Than delta t. So then, of course, there are constraints to your problem. So you cannot just choose any grid spacing. Yeah, you want to have a certain accuracy, or at least accuracy. So this means that you want to do the simulation in the limit of these things going to zero, which is of course bad news for cost. Yeah. You have a problem specific Reynolds number. And in principle, if you would do acoustics, you would also have a problem-specific Mach number. But most of the time, we do not do acoustics, and we do not care about the Mach number that much. But if you care about your Mach number, your analysis will be different. Yeah. So okay, I've forgotten something. We have a CFL condition. So the CFL condition, even if you don't care about your Mach number, it's there's a maximum speed, so a maximum relation between delta, so a specific relation between delta t and delta x, yeah, or a limit. So okay, if you will, you put this up here. So the problem-specific Reynolds number actually gives you there's a kinematic viscosity of your fluid and your problem. So we have said that with the star, we mean the one with the dimensions. It's not a beautiful star. Okay, epiphania actually means when the star appears above Jesus' birthplace. Yeah, so we have to draw nice stars today. So the viscosity was theta. Theta is this one third. 1 over omega minus 1/2 delta x squared by delta t. So theta is the dimensionless temperature. And omega, we know from BGK, is the relaxation rate. Is rate with E or without E? With E, yeah, thank you. So, okay, now you see this gives us some constraint on the delta, or we want to translate our constraints to what this means for delta x and delta t. So we can take this and say this is delta x squared. So we'll solve for delta x. So we have the kinematic viscosity times delta t divided by theta 1 over omega minus 1/2. So then we have a Mach number. The Mach number is our velocity scale in real units divided by the speed of sound, and the speed of sound is the square root of theta with the dimensions of the lattice velocity, so delta x by delta t, which means we can write, so we put delta t to the other side. This is delta t being Mach number divided by velocity scale times theta times delta x. Now we still have delta x here, but if we put this into this, then we have delta x squared on one side and delta x on the other side. Yeah, so we can write delta x being the viscosity times the Mach number. So this here will go to theta square root theta velocity scale 1 over omega minus 1/2. So this 1 over omega is in the BGK method is more or less our parameter. So the parameter that we can choose. Or we actually have two parameters to choose. We can choose the Mach number I mean, we can choose the Mach number as long as we don't care about acoustics. Yeah, and if we say, and if it's not too large, yeah. And if we are in the incompressible limit. And the other thing that we can choose more or less freely is the omega. Yeah. So given the physical velocity u and given the physical viscosity nu, yeah, we can choose omega, and by choosing omega we modify delta x. Yeah. So and we can now put this back into this here and see that a similar relationship holds for the time step. So comes with u square 1 over omega minus 1/2. So these are so this is how delta x and delta t depend on Mach number that we choose and omega that we choose. And I remind you that nu and u are physical scales, so they depend on your problem, and you cannot choose them. So what does this mean for our cost? So if we want to have cost in terms of these things. So cost was the volume and the duration. There's a performance that depends on your implementation, delta x squared delta t, and this will be volume times duration divided by p, now by performance. And here comes what we just computed. Theta u 1 over omega minus 1/2, and all of this to the third power nu times Mach square 1 over omega minus 1/2. Okay, looks ugly, becomes this. So you see, we get our 1 over omega minus 1/2 to the fourth power, and this goes into divided by p. So here we actually have the viscosity to the fourth power, Mach number to the fifth power, and then we have this theta minus 3/3. So this is just a constant. Don't bother with this. So now suppose these things here are non-modifiable. Yeah. So they volume, duration, velocity scale, they are not modifiable. Viscosity is not modifiable. P in principle is modifiable, but only with, better, computer or better. So what we can choose in terms of parameters is 1 over omega minus 1/2 to the power of 4, or we can choose the Mach number. The Mach number is also a big lever. Yeah, it goes with the fifth. Actually, I'm surprised about this. Yeah, that it's really like this. Okay, so yeah, but I mean we cannot make the problem is, now you see there's Mach number by the power of 5, but anyway, Mach number must be very, very small. Yeah, so it's a big lever, but it doesn't have a lot of, it doesn't have a lot of way to move. Yeah, so apparently this 1 over omega minus 1/2. So if we put omega to 2, cost is 0, right? I mean, it's always like this. If cost is 0, then also what you get is 0. Yeah. So the closer omega is to 2, the lower the cost. Can we actually use this? Now, going back to BGK, the one that we've implemented, yeah, how does BGK look like? We have our, okay, say in 3 dimensions. So we have post-collision population is the pre-collision population plus our relaxation parameter into Fij k equilibrium minus Fij k before the collision, and now we want to have omega going to 2, and this would be Fij k equilibrium minus Fij and now you see if you compare these two things, what you basically see is you do an inversion. Yeah, so it's exactly, this is the non-dissipation limit. So it's funny that there are applications where this works, but this definitely doesn't work with fluid dynamics. So I've seen a lot of simulations with linear collision operators and specific boundary conditions where this actually works, putting it to 2. Yeah, so no dissipation. It's possible, but not in general, not for nonlinear systems. Yeah, so this is a no dissipation limit. So in fluid dynamics is by definition not well behaved. BGK with omega, yes, we see that sometimes it works to 1.95. So there's omega. So if you run the lid-driven cavity problem, then you would roughly go to 1.95. Other problems would maybe having a different. So if you go this far, they usually get unstable. Now, the big question that is actually the topic of today is how do you get, yeah, I know we have already covered half an hour just to get there. It's often that way. How to get closer to omega being close to 2 without losing stability. So this is really an important question from an industrial point of view, because industry uses a lot of simulation. Yeah, so you make omega going closer to 2, you can drastically reduce your cost. Yeah, so now what to do? Yeah, so what we are going to use is our knowledge from asymptotic analysis that I hope you enjoyed last time a lot. So we did it in 2D, BGK. You know more about Lattice Boltzmann than most people using Lattice Boltzmann if you can do an asymptotic analysis. And if you understand everything this lecture, you will know even more. Yeah. So I remind you, one of our results, intermediate results, was this Navier-Stokes equation in that form, that we had the first order of the moment m10, yeah, with an overbar on top of this. And here we had this second order of the second order moment, dy, and the other second order moment to second order, and here we have something that would be a forcing term, and this is equal to 0, all of that. So, of course, this is the Navier-Stokes equation, because this m10 to first order is rho to the 0 order times u to the first order. And the other things that we have here, so these moments, m to 0 to second order is m to 0 equilibrium minus 1 over omega minus 1/2 into this collision term of the second order moments. And m11 to its second order, yes. m11 equilibrium again to second order minus 1 over omega minus 1/2 omega 11 to second order. So this is where this omega, I mean the small omega appears, this relaxation parameter, yeah? So there are only second order moments where it appears. In the asymptotic analysis. But in the code, it appears to all moments. Yeah, so we apply it to all moments, but relevant, it is only to the second moment. Yeah, so now obviously you see, the question is, we can apply this only here and do something else somewhere else. Yeah, because in BGK acts on all moments. Actually, you could say that's a good thing, because otherwise we don't know what to do with the other moments. But we are being lazy here. We just say, because we don't know what to do, we do the same thing with this again. But the Navier-Stokes equation does not specify what should happen to the other moments. They are irrelevant. So the idea is that they still have to relax, so they are not say they are not conserved, yeah, but they can relax with a different rate. So relax different moments with different rates. So this is our idea. So what's to choose here? Okay, let's first of all look at these guys that we have here. Yeah, the things that we actually want to relax, these guys here. And we start with omega 11 to second order. So what is this? So we've derived this last time to be the derivative in x of the velocity in y to first order and rho 0 to 0 order plus dy u x velocity to first order and rho to 0 order. This omega to 0 to second order we identified as, I'll take the rho 0 out, dx u to first order plus theta dy v to first order. So now what we observe here is that we have u x velocity derivative in x direction and plus the y velocity derivative in y direction, which is the divergence which we have identified to be to leading order to be 0. The divergence of the first order of velocity is 0. Yeah, however, this thing here is not 0 because theta is not 1. Yeah. So this doesn't help us. So let's rearrange this a little bit to see what happens. And what we do is we take omega to 0 to second order plus omega 0 to second order. And if we do this, obviously what we get is rho to 0 order 1 plus theta dxu 1 plus dy v to first order. Now we see that this here, and I mean, of course, this applies only to the first order, yeah? But at first order, this thing here is 0. So this thing, so the sum of the two, they do not appear in the Navier-Stokes equation under diffusive scalar. This means that the relaxation rate of these two things together does not matter to the Navier-Stokes equation. Yeah? So omega 0,2 plus omega 2, 0 does not show up at leading order. So, but they just don't show up together. So we have to do something else. We also have to look at omega 2, 0 plus, not plus, but minus omega 0,2. So this gives us 1 plus theta rho 0, and here comes dxu 1 minus dy v1. And this obviously is not 0. Yeah? So we'll have to keep this. We have to keep the difference between them, but we don't need to have the sum. So this guy here influences leading order. So now we can choose different relaxation rates for these things, but we have to do it like this. We have M20 plus M02. These two together, they do not depend on this omega that we use for adjusting the viscosity. So we can give this another omega and we call this omega p. Then we have M20 minus M02. Now this appears in the Navier-Stokes equation. So what we have to do is we have to get the omega bgk here. And then we have the moment M11, which also needs the omega bgk. So now we have identified that there's actually, so we have 3 different moments. Yeah, we have to rearrange them, 3 different second moments. We have to rearrange them a little bit, having actually an isotropic part and a non-isotropic part. Yeah. And 2 of them would have the relaxation rate of the BGK and 1 can have a different one. So, are there more? Let's look at the grouping of moments. And here we go by the simple example of D2 crew 9. Get a little bit more involved later. Okay. So we have M00 and M10 and M01. They are conserved. So they do not require any relaxation. Then we have M11 and M20 minus M02. They are non-conserved. Hydrodynamic. So hydrodynamic meaning they appear in the Navier-Stokes equation. They use omega BGK. Then we have this M20 plus M02. Yeah, we have identified this as being the pressure. Yeah. So actually it's the total pressure, including dynamic pressure and the what is the part that is not, what is total pressure minus dynamic pressure? What is the other one called? The static pressure, yeah. So this is the total pressure. And also this is the acoustic moment. This uses now this omega p, and this is related in physics. So I mean, real air is not incompressible, yeah. And we have acoustics, otherwise you wouldn't hear me. So this is related to something that's called the bulk viscosity, and this is an annoyance in science because this is not well defined. I mean, it's not well defined in the sense that it can be defined in different ways. The similar way how you define pressure in different ways. Yeah, so you can include some part of the shear viscosity within the bulk viscosity, or only so there are different non-consistent definitions. This is one thing. The other thing is it is not easy to measure, and it's not very it's not very constant. Yeah, it's not. It depends on a lot what is in the air, in particular in the moisture. So the moisture maybe is not the big deal. The big deal is that whenever you have moisture in the air, you actually have partial condensation. So you have small droplets, and the vibration of these small droplets influences the bulk viscosity a lot. So you may have noticed that if you are in smog or in dense fog, that sound doesn't travel as far as in clear air. Yeah? And this is due to bulk viscosity being higher if there are particles in the air. Yeah? So it's different. So usually you don't have a good feeling what this should be. And so don't believe anybody who is telling you that the bulk viscosity should be the same as the shear viscosity. That's not true. Yeah, it's just difficult to specify what would be correct. So what this does is doing damping of sound waves. So then we have, in addition to these guys, we have our ghost moments. And there are 3 more missing. So this is M21 and M12. These are the third order moments, and I will just give them the relaxation rate omega 3. And to the fourth order moment M22, I will just attach the omega 4. And this are our ghosts on this lattice. So this lattice doesn't have a lot of ghosts. So now there are lots of different things that you could potentially do with omega p, omega 3, and omega 4. But one idea that is kind of obvious is that you use them to increase the dissipation that does not associate with viscosity directly, right? So, like damping sound waves without damping shear waves. Yeah. So you can suppress pressure waves if you put omega, say, close to 1, setting it to equilibrium. Yeah. And you can suppress the ghosts. I mean, this is an idea. It's not necessarily true that this is the best solution, but this is an idea that you could have. Yeah. So, by the way, you will find in literature spaces where they say that when you put omega p equal to 1, all the stability improvements of MRT or kind of MRT models is due to putting bulk viscosity, to ramping up bulk viscosity and suppressing pressure waves. This is treated by some authors like a dogma, and it certainly has its merits. So by removing pressure waves by high damping, you increase stability. But it has not been demonstrated by these authors or by anybody else that this is all to it. Yeah. So yes, you can. I mean, this is an important thing, but there is a little bit. The reality is a little bit more complicated than just putting pressure waves down. So let me see how going on. Yes, we have the classical MRT in 2D. That's due to a paper by Lemont and Liu, and this was in the year 2000, and it was in Physical Review E61. 6 on a page, it was 6546 if you're interested. So they introduced these MRT methods, the classical MRT method, which is now, of course, as you see from the time, not state of the art, so we can do much better than that, because we have a better understanding of what went wrong back then, but this is already a relatively well-performing model. So the way this is classically done is we use a transformation through an orthogonal matrix. So we have a vector m, so which is the moment vector, that is obtained by multiplying m by transformation matrix m by the population vector. Then you do the collision in terms of the moments and the streaming. So what you do is you use, for streaming, you use populations f, and for collision, you use moments. So once you have collided the moments, what you do is you get the post-collision populations by using an inverse matrix on M. Yeah. So please don't implement this. This is very inefficient. Yeah. I mean, this is how, in principle, it works. Yeah. So the matrix M here used an unweighted. So we've talked about this already sometimes. Yeah. Now we're getting closer and closer to why this is important. It uses an unweighted orthogonal matrix M. This is used. Okay, and this led in this into a certain nomenclature. D2Q9 moment system. That looked like this. So this M was a vector of the quantities rho. So rho is the one that is obvious. This is the zero order moment. Yeah. Then there is, I find this ordering very strange, but this is how they did it. So now they have E. E is supposed to mean energy and is basically the pressure. Then there is something that they call epsilon. Epsilon is energy, what they call energy square. Then they have Jx, and Jx is supposed to be a momentum in x direction. Then they have a Qx, which is something which is supposed to be the heat flux, which is very inaccurate for this model, but this is okay. This is the closest physical quantity that they could master. Then there is Jy, which is the momentum in y direction, Qy, and then there is Pxx and Pxy, which are shear moments. So I will not write down the matrix. Instead of writing down the matrix, which you find in the paper and in a lot of papers that followed this paper, yeah, so this paper, of course, has thousands of citations. Yeah, I'll do it more in the nomenclature that we learned. Yeah, and using countable raw moments. So if you write this in our moments, so rho would be m00. Yeah, very simple. E is not really the pressure. Yeah, it's 3 times m20 plus m02 minus 4 m00, and this is supposed to be the acoustic moment. And I mean, not being nice. Now, if you think this looks stupid, this is because it is stupid, and later we'll understand why. Yeah. So this is so the pressure would actually be only this one here, and they take it times 3, and then they subtract the zero moment. So epsilon is 4 times m00 minus 6 times m20 plus m02 plus 3 times m22. This is a ghost. You see a lot of mixture in here. Yeah. Then Jx, so this is momentum. This is conserved. Nothing to worry about. So Qx is, yeah, kind of the heat flux. Not really. 3 times M12 minus 2 M10. So this is also a ghost. Then we have Jy is M01. I'm using the original ordering, by the way. Q y is 3m2 1 minus 2m01. Again, a ghost. Then here in the end we have the important things. This is pxx is actually m20 minus m02. Yeah, you've learned that this is the hydrodynamic thing that we have to worry about. And the other one, pxy, is equal to m11. So these are hydrodynamic. So here, these are the ones where we have to put omega bgk. So how on earth did they come up with these numbers? 3, 4, 4, 6, 3, blah. So this is all due to the unweighted orthogonality. Unweighted orthogonal. So now there is a little bit of problem, a didactic problem. In principle, nowadays we don't use unweighted orthogonality usually anymore. Yeah, but if you when now you learn Lattice Boltzmann, you will find these papers have tens of thousands of citations because they came up with this, and this is of course, I mean, they deserve having these, but you also have to know that not everything that they thought back then is still, you know, the right thing. So now you have to get an understanding why they thought it was like this and why we now know that it is not like this. So unfortunately, we have to go through these steps. Yeah, even though in the end, maybe you just, you see, the problem is that that you always that even after decades, people dig out old papers and try to start from this point. Yeah, which is may not be the best the best solution. Okay, unweighted orthogonality. We've already discussed this, but we are coming back to it. So we have a moment, some moment m phi, that is defined as now in two dimensions as the sum over I and j with a kernel phi ij until fij. And then there is another moment, say m psi, that's defined as the sum over I and j over a kernel phi psi ij fij. Yeah? So, and these two things are unweighted orthogonal to each other if their kernels have this property ij phi ij psi ij equal to 0. Yeah, that's the condition that makes them unweighted orthogonal. Yeah, so it's unweighted because there is no weight in this sum. Okay, so the spoiler why this is a problem is that the f's, depending on their direction, have very much different values. Yeah, so the orthogonality that you put by just making the matrix orthogonal without considering that some of your data is much larger than other data does not really cause independence. Yeah, So if you want to make your data kind of, if you want to have a transformation, making your data independent, then you also have to take the size of your data into account. If this makes sense, if not, follow me through, okay? So the example, okay, does this work? Example. So we have E is equal to 3m20 plus m02 minus 4m00. Yeah, so this can be written as the kernel. So what we can do is, because these moments are linear transformations, so we can add up the kernels that will produce these moments and multiply them by f, because they are linear, right? So the kernel that we have here, 3, so kernel of m20 is obviously I squared, right? Clear? Yeah, plus j squared. And this minus 4 times, so m00 is 1, yeah? So that's the kernel. So this goes into Fij. So, but this means here, this for example would be our kernel Psi ij. This would be the one here. And seeing whether this is orthogonal to rho would be ij from -1 to 1, Fij. So now there is no I anything, which means that for this, the kernel, call it psi, ij would be simply 1. Yeah? So now E would be orthogonal to rho, unweighted orthogonal to rho, if we have I and j from -1 to 1 into psi ij, phi ij, psi ij. Now, I mean, I was a little lazy using the simple example, but still, see the following. We can put here 3i squared plus j squared minus 4. Now this we have to multiply by 1, because the other one is just 1. And then we sum this up and get 3 times 6 plus 6 minus 4 times 9, and this gives us 0. Yeah. So this is how we know it's orthogonal. Yeah. So this is unweighted. They are unweighted orthogonal. So what they have done, what they have done with the E is that they made it orthogonal to rho. Yeah. And they actually don't explain why. And I mean, this is this has taken up a considerable part of my life, I have to say, to figure out what that means, and an even larger part of my life to actually discuss with these people who had these ideas and their followers. Yeah, because they, in particular, their followers thought that this is very important, and it is not. Okay, so there is some, this model works very well, and the reason for this is talking about things that work very well. So the reason why this works very well is because this lattice has only 3 ghosts. So the small number of ghosts simplifies our life a lot in this, and this is a bad thing because I mean I'm bashing mathematicians here. You've noticed, right? Let me finish the sentence and then I go on bashing. Okay, so this has little effect. And this is different in 3D. Okay. I should not talk about all mathematicians in the same way, but one thing that I notice is it's often preferred, I mean, to simplify, I mean, this is true and important. You want to simplify your problem as much as possible. Yeah. So you try to solve it in as few dimensions as possible. So basically, if you can do anything in 1D, you try to do it in 1D. And then if this doesn't, or you try to do it in 2D, and then only you go to 3D, right? And maybe even, and if you are running out of ideas on writing papers, you go to 4D, yeah? But, okay, so what's the problem with this? Now you see, for example, you see this example in 2D. You see good results with unweighted orthogonality, and then you conclude that you did the right thing. And you also conclude that taking up one more dimension is straightforward. And so when I was young to this 20 years ago, I always read that the extension to 3D is straightforward. Fortunately, this sentence has disappeared from literature, most likely because nobody bothers about 2 dimensions in fluid dynamics anymore, which was different back then. And the second thing, it's not true. Yeah, it is not true. Things completely change. Yeah, and now let's have a look. Let's have a look at this. So we go to D3Q27 lattice. And here we already find a problem here. There is no classical MRT in literature. Maybe you know, not the classic way. Yeah, maybe in the last, I guess, in the last 10 years there may be some, but they are different from just extending the 2D. So now this is maybe your homework. Guess why, or maybe we'll come to this. Guess why this is the case. So, I mean, I can give you one thing. You will always, science has a problem. I mean, science has a lot of problems because only people talk about money. They are not concerned about real science. And the thing is, in science, actually, you can only learn something from failure. Yeah, that's the truth. But you can only publish success. and the thing is, so I've talked to many of the old folks there, and they just said, "Oh, I've never done this." And maybe it's true or it's not true. The thing is, I certainly believe, because I've seen these things going on a lot, I certainly believe that many PhD students or in-betweeners somehow, yeah, try this out, and then they try to run it, and then they failed. So they say they didn't get a result. And then they thought they just made a small, so, okay, I made something wrong, because you can never prove that I mistyped something. And then they abandoned this, or their professors told them you're stupid, yeah, depending on the way the social things work in these institutes. And so simply it never came into being for this lattice. So what you will find is D3Q15, D3Q19, even D3Q13, but no D3Q27 MRT. Say state 2050, I would say, yeah? But from then on, we have a better understanding, and now we know how to do this. The problem back then was that we just wanted to extend our ideas from before, and this didn't work. So let's look what is the problem. So here we have to use our grouping of moments again. So of raw countable moments. So what moments do we have? We have M000, M100, okay, I'll not repeat everything now, but M001. So these are all conserved. So these things do not need any relaxation. So there may be forcing terms that make things a little bit different, but we are not talking about this today. M110, of course, there are permutations, and there are 3 permutations of this, right? And then we have M200 minus M020 and M200 minus M002. So when I was your age, I was terrified by having 3 of these and 2 of these, because we can arrange them in different ways. Doesn't matter, yeah? So these are the hydrodynamic guys. Hydrodynamic, and they would have omega equal to omega BGK. That's a given. So then we have the guy that is related to the bulk viscosity and pressure waves, the acoustic moment, and here we would put omega p, and this would give us a bulk viscosity. And again, in physics, bulk viscosity is not equal to shear viscosity, but is something that depends a lot on the state of the air. So this is basically where we have our physics, yeah? And you see, due to the cause of dimensionality, we have much more ghosts. So in 2D, we had 3 ghosts, yeah? It's not that we just get, so now how many do we have? 1, 2, 3, 4, 7, 10, and no, it should only be 10. Where do I see? What did I do? It should be 10. So this is 4, because these are only 2. Yeah, it should be 10 hydrodynamic moments, yeah? So, and then we get a lot of ghosts. And if I would be able to write ghosts. So there are classes of ghosts, and I will name them by their order of the moment. So there is, at 3rd order, we have 3rd order A is M120, of which we have 6 permutations, yeah? Then we have 3rd order B, M111, of which we have only one permutation. We have first order A, M220, of which there are 3 permutations, and first order B, M211, of which again we have 3 permutations, and then we have three permutations of 5th order moments, and then we have 1 6th order moment, M222. Anything more? Oh, I did.
Is there
Yes, sorry. Yes. This was for what you wanted. Yeah, thank you. Okay, good that you are always watching me. So, first of all, these things are not yet in the right state, and this is another thing. Can they be further subdivided? Actually, this much later turned out to be very important for a reason that I'm not going into today. The subdivision of these things. So yeah, okay. What is the time? We have a lot to cover today. I'm sorry. So I mentioned that this pressure moment was an isotropic moment, right? So what I meant by this is that in any orientation of our coordinate system, it would always come out the same moment. So this is obviously not true for all of them. Like obviously in a, I mean, the very obviously, if you the first order moments, M100 and then 010, if you rotate this by 90 degrees, you would turn M100 into M010. Yeah. So now you would identify, if we are living in an isotropic world, that these two things would be of the same class. Yeah. So things would be of the same class if you can turn them onto each other by rotation, physically speaking. However, there is a catch even to this, and I mean this is now I'm going against the claim that I did in my PhD thesis. Because in my PhD thesis I ordered everything physically. So saying, suppose the world is physical, so we can turn things onto each other in the physical world, assuming that the physical world is isotropic. But then we also have a lattice. Yeah? And then so you can have moments that you can turn on each other in an isotropic world, and then there are moments that you can turn on each other only in a discrete world. And also they behave differently. Yeah? So, and also they can be separated. Okay, now, in order to see this, what we have to do is we have to apply rotations on our moments. And I'm not, for the time that we have here, I'll not do this in a lot of detail. I'll just give you an idea, and then if you're further interested, you have to do it yourself. So, a rotation of moments. So say we have this xi as our velocity in the lattice. So this as a continuous velocity, but on the lattice, this is given by the vector ijk into delta x by delta t. So this is a velocity on the lattice. Yeah. So and this is of course given by I times the unit vector j in these different directions, and is multiplied by delta x divided by delta t. So suppose we define a different vector I r, j r, and k r as being the rotation. So there's a rotation matrix applied. So I'm mixing up a little bit nomenclature here. Yeah, I hope you're not too much worried about this. So this is our matrix, two lines below. On this vector can now be written as the rotation applied to the x vector multiplied I plus j on the rotation of the y vector plus k on the rotation on the z vector. Okay, this just I noticed delta x. So in principle, I have to multiply in order to be consistent by delta x and delta t. So now what would be these rotations? I believe I'll have no business explaining what a rotation matrix looks like. Just we get one example, one standard example of Rx being equal to 1, 0, so the rotation about the x-axis, yeah? So it has one here, and then they have the cosine alpha minus sine alpha at 0 and sine alpha cosine alpha. So this is a rotation by alpha. So we've all seen this a lot of times. So now the isotropic the isotropy of the acoustic moment. So M's, call it MP. MP is the sum over ijk is equal to minus 1 to 1. And so, you know, because it's a linear transformation, it's I square plus j square plus k square into fijk. Yeah, you see this. Anything on that's clear. Yeah. So now the thing is, for any rotation, so for any matrix that is a rotation matrix, what you get is that this sum, yeah, so because this is the length of the vector, yeah, and the length of the vector is conserved under rotation. So this means that it's the length of the vector squared, yeah. So this thing here will be the same as this here. Yeah, so and therefore this thing will be isotropic. Okay, now this is something that we already know. Let's see what we probably didn't. Okay, maybe looking at the others. Yeah. Let's look at the moment M210. So what isotropy properties does this have? Now let me just add to this M102, and this would give me sum over ijk minus 1, 1. So, okay, what is the kernel for this? So what is the kernel for the first one? Ij squared. And for the second one, ik squared. So I'll write it like this, right? Fijk. So let's apply a rotation. So that this is not isotropic under any rotation, but it will be isotropic under specific rotation, and specifically under rotation about x. Yeah? So this means when we rotate about x, then IR, because I is the one for x, will just remain being x, and JR will become J cosine alpha minus K sine alpha, and K, when rotated, will become J sine alpha plus K cosine alpha. So let's look at IR IRJ JR square plus KR square. So I mean this is the kernel under the. I mean I was potentially I was you see this is true without the sums, yeah. That's the point, yeah. Sorry for this mistake, yeah. So we look at this under the sum, right? So when we do the replacement of this, and it's I, so IR becomes I, and the other ones are just what is written here. So they are now square, so this is J square. So then there's cosine square alpha plus sine. So I take, okay, this cosine squared, yeah, and am I doing this correct? Okay, I'm writing it down and see, plus K square sine square alpha. So I have to admit I'm just writing it from my notes. Yeah. So then, but what you observe with this is that this here is 1 and this is also 1. Yeah. So which means you will end up with ij square plus k square, which means that this thing here is invariant under rotation about the x-axis. So, however, the same thing does not apply to M12 minus M102, because here we'll have IRJR square minus KR square, and this goes into IJ cosine square alpha minus sine square alpha plus K sine square alpha minus cosine square alpha. So these things here will not disappear, so they are not invariant. So we can, so these two things behave in different way. Yeah, so we can, so they are physically different things. So they can be separated and they can potentially relax with different rates. Yeah. So we'll have different groups here, more than just the two that we have identified. We actually have three. So we have the group M120 plus M102. Of these we have three, and we give them the relaxation rate omega 3 plus. And then we have M120 minus M102, 3 times, and this is omega 3 minus. And then on top of this, we also have M111, which we give omega 111. And I am on record to put this into this group because physically we can rotate the one to put on the other. But if we rotate the lattice in this way, the lattice does no longer fit onto each other. Yeah, so you have to rotate in the wrong angle. So we actually have to distinguish between these three things, and the reason for having three instead of only two is that our lattice itself is not isotropic. So for the fourth moment, we have M220 minus M202, of which we have twice. Call this omega 4 minus. We have M220 plus M202 plus M022, omega 4 plus. Okay, we have M211, of which we have 3 times. I have written something wrong here, so let's say this is, okay, I'll call this omega 211. Then we have M221, of which we have 3 permutations. We give omega 5, and we have M222, which is just one moment. We give omega 6, and altogether we should have, I'm not going to count them now, we should have 10 relaxation times, relaxation rates. So, okay, 1.5 hours, but we still have something important to learn about the unweighted orthogonality. So unweighted orthogonality works very well in 2 dimensions and in some of the lattices in 3 dimensions, but not for that lattice. And we'll see why. Okay, we have to recall the asymptotic analysis. So we have MABC to second order is equal to MABC equilibrium to second order minus 1. Okay, so I'm lazy here because I know that's not necessarily directly MABC, but to that particular moment, we'll assume that there is a relaxation rate omega ABC. So this does not apply to the grouping, obviously, very well. So, and then we'll have MX. So now you have to remember, here we go 1 up, yeah? So we'll have 1 order more. And in the indices, we also count up with the derivatives. Yeah, so have A plus 1 BC. Yeah, so this is something that's the beauty of countable moments. M first order A B plus 1 C and M A B C plus 1 and this to first order. So this is how this works in general. And now specifically, say we put A equal to 2, B equal to 1, and C equal to 1. You see, this is a ghost. Yeah, we are talking about the ghost because the ghosts are spooky. So this is a first order ghost. So how does this first order ghost behave? M211 to second order is equal to M211 equilibrium to second order minus 1 over omega M211 minus 1 over omega 1/2, yeah. So dx, so now we get 311 first order plus dy M221 plus z M212 to first order. Okay? So now we have to identify these things. So we'll have two guys of this kind. So fortunately, we know very quickly how to compute the equilibria here, yeah, because you have learned this, so we can factorize this, right? So when we factorize this, we get, okay, actually, we have to write out all the possibilities, yeah, but you already see that there are not so many possibilities because the ones here, they need to be first order, so the later ones, yeah, they need to be first order, otherwise they would be 0 and they would be disappearing. So the only one that would not be 0, that is not 0 at 0 order is when something is here, comes with a 2. So we can write this as M200 to 0 order times M01 to first order, M001 to first order, and all of this divided by M00 to 000 square. 000, okay, to 0 order square. Yeah, that's how it should be. And this we can identify as rho to 0 order theta. So this comes up here into velocity in y direction and velocity in z direction, which we write with W. Now, what's about these guys? So these guys, to first order, they are all equal to their equilibrium. To equilibrium, they are all first. Yeah, so there's no non-equilibrium first order, right? You remember, yeah? So this means that we have, and on top of this, so, I mean, this is an alien and a ghost, right? So it's an alien, meaning this becomes M11 to first order, and to first order, this thing here is 0. Because if there's no non-equilibrium part to first order, and if you write down its equilibrium to first order, only one of them could be non-zero, yeah, and so it will disappear. So M211, we are already to first order, we are in exercise time already. Can you tell me out of your mind what this would be? Okay, so similar to the one above, right? So we get from M200, we get the theta. Now we have two of them. So we get theta square. We always end up with 1 rho 0. And then we have V to first order. The one that was missing is M1, so that one, yes. So that one would obviously be W. Okay. So first thing is, suppose we forget about orthogonality altogether. Yeah? Because nobody ever explained why they should be orthogonal, even though there are big beliefs in this. But we don't want to be. We want to be religious in church, but not in science. Yeah. So suppose we don't care about orthogonality. What happens? Say we'll get equation 9.1 and say we have M211 to second order is equal to theta rho 0. So that's the equilibrium part. W first order minus 1 over omega 211 minus 1/2. And yes, what we identified further on was theta square rho 0, and here we get you see the derivatives of these moments, right? I put theta square in front because it's and rho in front because they are constant. Yeah. So what is it? dv dy w to first order plus dz v to first order. Does this already look problematic to you? Why? Why do you not?
If there is a partial derivative to x and with the u
to x, there is no partial derivative with x. There's only one with y and with z.
Yeah, if we have another with u, then it can be 0.
Okay, but we don't have another. The point is we don't have another one here, so this cannot be 0. I mean, I'm not so much worried about zeros. Zero is a well-behaved number as long as you don't try to divide by it. Okay, I'll make you divide by 0 in 5 minutes, okay? So let's see. This should be familiar to you because we have this in the hydrodynamic moment. Yeah, let's have a look. So the hydrodynamic moment. We have the hydrodynamic moment M011, yeah? To second order, the same order, yeah? So you know this moment as the one that gives you the shear. Okay, let's have its equilibrium. Its equilibrium is rho 0 V to first order W to first order minus 1 over omega. It's hydrodynamic. It comes with BGK. Minus 1/2. And then it has theta, so now only theta, rho to 0 order. And here we have dYW1 plus dZV to first order. Okay? So, what's the problem? Now we have two moments showing us the same thing. Okay, they may have a different prefactor here, yeah, but otherwise they give you the same thing. So why is this a problem? The problem, yeah? Yeah, okay, I mean, if they have the same thing, they are dependent, yeah? So, now what is the problem? You decided that you want to use MRT. So you decided that they evolve on a different time scale. Yeah? So what does it mean? Let's have a look. So basically, I mean, this thing here is something that comes out of your simulation, this later part here, and this is showing up here again, right? So what I'm going to do now is to say there's this theta, rho 0, dYW first order. So this is, if I put it the other way, is M011 to second order plus I've taken this minus here in front. This is why I have a minus in front of this, and while I'll have now a plus here, because I put this on the other side. V1, W1, and this divided by 1 over omega BGK minus 1/2. So now I know what this is, right? So I put it into 9.1 and see that M211 to second order is, of course, its equilibrium thing. Minus. So it has this 1 over omega 211 minus 1/2 in front. We divide by 1 over omega BGK minus 1/2. And because there's one theta more, there's a theta left here. And we'll have minus M0 to first order plus rho to 0 order V to first order W to first order. Okay. So what's the problem with this? Well, the problem is, so there is something that's given by physics. Yeah? This one is second order, you're right. So this one is second order, yeah. So, but this thing here is given by physics, yeah. That's the shear rate. So this thing here exists, and it's not necessarily small. Now you have made the decision, or you potentially made the decision that you want to dampen this moment here by putting this here close to 1. Meaning that this here is much larger. So because what you want to do is you want to put this here to 2. And you want to put this here to 1. Or close to 2, close to 1, right? In order So your idea was, if you do this, you make this guy here small, because you had the intention, you had the well intention to dampen it. Yeah? But what happens? So if this here, yeah? So your intention was to make it small. You were not successful. Yeah? So because, I mean, BG in, or let's say there's a difference, or see what is the difference in BGK if you have BGK. If you're using BGK, that would be true, right? So this here would be 1. So you have these two guys, they are proportional, they are of the same, I mean up to factor 1/3, the same, okay? Nothing big to worry. In MRT, what we want to do is we want to get this closer to 2, while the ghost thing, we potentially want to put to something else. Meaning that 1/ω2 minus 1/2 divided by 1/ω BGK minus 1/2. So this guy goes large. And the thing with the ghost is ghosts are not harmless if they get too big. Say this is a big ghost. So, however, this has taken more than 5 minutes, I know. However, this is when we don't use orthogonality. Yeah? So now the idea is, if we use orthogonality, the dependence of the moments will disappear. Okay? Let's have a look. Unweighted orthogonality. I have this problem that, I mean, I can make this orthogonal, but I would like to talk to the because I'm going to destroy this thing. I had to ask a mathematician who was working on this, give me a matrix. Then I use your matrix, yeah. And even though I showed him that this crashes, he never accepted this, and now he's retired. Okay, I asked somebody else for a matrix. He's a very nice guy and he's had a lot of useful results and so, but just because I was bashing, I'm not using his name now. Okay, and I learned a lot from this mathematician. And we only learn from failure. So in this matrix, there was this replacement moment, unweighted orthogonal moment, that comes from being M 213 M 211 minus 2 M 011. So what you see is we do something together with the two moments that we found being dependent on each other. So this looks good, right? So now what we can do is to write down N211 to second order over bar. Now we just replace these. Yeah, we sum these together. So there will be 3 times M211 equilibrium to second order minus M01 equilibrium to second order minus, so this guy would relax with omega g, and I will take rho 0 out. So we'll have, okay, so they both have the same part with the derivatives. They just differ by having 3 theta square, so this comes from the first one here, minus 2 theta, right? And this goes into y first order plus this first order. I should close these brackets too. So by putting in the same thing for this non-equilibrium part back here, I can write this being as 3 M211 equilibrium to second order minus 2 M011 equilibrium to second order minus 1 over omega g ghost minus 1/2. So we'll have a similar thing here going on again. Omega bg k minus 1/2. So you see this thing here does not disappear. Yeah, so have so it is okay. So what the one thing that disappears, it disappears together. So one theta here is disappearing. Yeah, so here is theta square minus 2 theta. Yeah, so we'll have only 3 theta minus 2 left, and here we have M011 to second order minus rho 0 V1W1. Okay, there is, the thing is still here. There is, practically speaking, a very drastic difference between these two things, even though both are very bad. Can you spot what would be the difference between this one, the weighted orthogonal, and that one? Let me see, I hope I have not killed it. Oh, let me see whether I did it correctly. Okay, there should be in my memory, but I'm an old man. So this goes plus. Okay, no, forget this. I don't see this point. Okay, forget. There is a difference, but we don't see it at this stage. So forget this point. It's not important. I mean, it is important for a practical point of view, because it behaves. So these two models behave very differently, but it's not easily visible from here. So the bottom line that we see is that this is still, that we still have a large a large ghost. Okay, so I told you that this person never agreed with me that this will kill this model, because the thing he simply said, well, okay, if you have this problem, all you have to do is to put omega g to VGK. And then it works. But that was not the point. Yeah. So we did this so that we don't need to do this. Yeah. So empirically, the behavior of these two things is different insofar as what happens in the non-orthogonal case, even though I was thinking that we see this directly here, but we don't. What happens in the non-orthogonal case is that we observe excessive overdamping, meaning that model is incredibly stable. Yeah. So if you have so whenever you have some artificial damping in your system that is unphysical, then this usually means your model is stable. So this can be regarded as a big advantage of the non-orthogonal way. Now, because we turned here some things around, this overdamping in this overdamping in the non-orthogonal case will in the orthogonal case have a negative damping. So what does negative damping do? It kills PhD students. Yeah. So think about this poor PhD student who the professor says, "Oh, there is no. You want to write a paper, so there is no MRT for DQ27. Try it out." So it tries it out, crashes, doesn't know what to do because he was told you need to have unweighted orthogonality. That will not work because it has negative damping. Yeah, so it's a very, very delicate model and not good at all. By the way, D3Q19 works very well because it does not have this moment. Yeah, this is why it works. So now we are not going to leave here with this sad result because we actually know what to do, and maybe you have seen enough that you can guess what to do. Yeah. Okay, I'm writing this. This is an empirical observation by myself. I don't know whether I can prove this. So the MRT with the unweighted orthogonality is even less stable. Actually, the non-orthogonal, as I said, the non-orthogonal has no problems with stability, even though it has a large ghost. It just overdamps. So now in these old papers, they will never talk about unweighted orthogonality. They just say orthogonality. Yeah, I make the point that they use a specific kind of orthogonality. So then there is, of course, a weighted orthogonality, or you can weight your orthogonality and then it will behave differently. So now, what would you do? Well, basically, you would look at what have I done. And you will see in this thing here, we'll have here 3 theta square minus 2 theta. And now you will think, so, well, this is under my control because I defined this moment this way. All right? And all my pain, as I said, 0 is a well-behaved number. Yeah? All my pain would be gone if this here just summed up to 0. So why don't I just put, so if this is 3, and there's 3 theta squared, so I know, there's a theta square in here and there's a theta in it. Then 3 theta is 1, right? So why did I'm just, instead of putting 2, putting a 1 here. It's my free choice, right? So let's have another moment called M211, being defined as M211. So the idea of this being, I use the factorization. Think about this. I use the factorization of this here. Okay, we have this M011, yeah, and now I factor out the equilibrium of this first dimension. This would give me a theta. So I define this here basically as the M, yeah, equilibrium under. This is not yet the optimal solution, yeah, but it's an intuitive solution that we can use. Okay, so when I do this, what happens? N211 over bar to second order is equal to M211 equilibrium to second order minus theta. What am I doing? Theta M011 equilibrium minus 1 over omega g, ghost, because I still want to relax this in a different way. So now I get theta square rho to 0 order minus, and here I get theta square again, rho to 0 order, yeah, because here I had theta square in this, and here I have theta in it. So I multiply one more theta, so I get theta square again. And all of this goes then into dx, not x in y, sorry. So derivative, so this to first order plus the sets with to first order. Okay, so now we don't care about this because it's 0. Yeah. Okay. Did this solve my problem? Now you could say, wait a minute. I just defined a different moment. So I can define a different moment that is 0. So what does it help me? It would only help me if by defining that other moment and relaxing that other moment, the other thing would be small too. The one that we had before, right? So let's look at, okay, getting this question. What does it mean for the non-orthogonal moment? Yeah, so just saying that I found the thing that is small does not help me, right? So let's do this. This guy here is nothing else than n to 1 to second order plus, because here it was minus, right? Plus theta m011 to a second order. And this is m211 equilibrium. So here there is no non-equilibrium part in this, as we have identified. Yeah. So all we get is theta m11 equilibrium plus theta 1 omega bgk minus 1/2. So we get something that's proportional that now behaves as it would behave in, as it would also behave in BGK. So this other moment does not go to 0, but it is as small as it would be in BGK. Yeah. So and this now is our small ghost. Okay, and this is something that I believe took a very long time for people to figure finally out and also to accept, because these models, these other models were well established for a long time. So if you go to Tim Krüger's book on the lattice Boltzmann method, this nothing. So they will discuss the different. So they will present the different possibilities for orthogonality as a fact, without any conclusions or consideration what this means, because this book was just published before there was a better understanding of this. So when you go to the book and learn from this, you're unfortunately missing a very, very important point. So, how late is it? So because we covered a lot of ground, I potentially have the idea that we should. Do you want to have an exercise? Okay, I mean, the logical thing to do now is to implement MRT into our code. Yeah. I don't. Do you want to do this now?
Yes.
Sorry, Daniel. You don't need to stay here. The students are killing me. Horrified. Okay, I have no idea where we are. So we left this. I guess this was our code, right? Okay, so far we had this. Okay, I'll have to change my setup here. So far we had this run function, and this run function does a BGK. It does a BGK. So what we would have to do is, I mean, without trying to be too clever, is we would have to kind of copy all of this and write including the swaps and so on, and defining this as a new run function for MRT. So first thing, which was at 213, so saying this was, we would have to run MRT. Okay, being lazy, being late, and so on, what I'm going to do is I'll put the other relaxation rates, just in the parameter list. Yeah, so we'll have 3 more of them. Yeah, because we have floats omega p. We'll have floats, the one for the third order, because even though we learned something about isotropy, none of this matters in 2D. Yeah, and floats you see the moment that we were concerned with is a moment that does not exist in 2D, right? Yeah. So it was very confusing. Yeah? This is I have some life stories to tell from this. So run MRT. Okay, we have this. So what we need to do is we have to compute our moments. So obviously we have already 3 of them, but we need another 6. So we'll have M20. Okay, what I'm going to do is I'm building these things up from from this one, because everything is in this, right? So I'll take, I don't know whether I can make this larger. Okay, so this is all of them, all of the populations. M20, what is M20? M20 is everything that doesn't has a 0 in the second index. So this here has a 0 in the second index. Right, so if we have a 0 in this, because we multiply we take okay, let me. So everything that's has either 1 or -1, right? But not 0. In the, I'm making something wrong, in the first index, Yeah. Not in the second, in the first, sorry. Yeah. It's dangerous to do this. So in the first index, so this would be that one. Okay, so a less dangerous way of doing this is use Mathematica to calculate them, right? Maybe I should do this. You see, I'm not prepared, so this is a okay, I was stupid. I should have not taken this one. My powerful enemies will use this against me. that I'm making a mess here in front of the poor students. So that will be everything that doesn't have a 0 in the second index. And the 0 in the second index would be that one. Okay, then we have the last, this M11. M11. So M11 is something that does not have any zeros in the indexes at all. Meaning we have to take these here out. So, however, it is when I times j. So mm minus minus is plus. Plus plus is plus. Minus plus is minus, and plus minus is minus. Okay. And here's a semicolon missing. 3 out of 6. Float M21. This did not work. I'm going to use Mathematica for the back transform. So that would be one that does not include, so the first, okay, so when the first index is 0, and we take it by the power okay, I mean, maybe I'm getting old here. Now my stupid computer does not allow me to increase the size of this. How can I? Okay, I have an idea. So say more A, B is the sum. Okay, so now we have to do our stupid old tricks, right? I plus AA, right? To by the power of 4 times J here. What is missing? F I and J. And we're summing over I from -1 to 1 and J from -1 to 1. So let's, was I stupid? So this is everything excluding the ones that have a 0 in the first index, right? This is what we said. So what is the one that we are currently bothered about is 2, 1. So 2, 1 has everything that has a minus okay, it has only the 4 in the diagonal, and it has everything that has a minus in the second with a minus, and the others with a plus. Yeah. So actually, we are best off taking this one because they already have the same content. So everything that has a minus in the second has a minus. Everything else has a plus. So we'll have to be diligent here. Otherwise, we'll kill ourselves. So meaning I'll have something similar for the other guy. Okay, so this minus will be here, and this minus will move to this here. Yeah. So we have no. I mean, you have to watch me. There's no safety net here. M2. M22 is, I think, the corners in. It's all the corners, yes. So what we are going to do is just copy this and put the plus here. But that will do. Okay, now we are not yet done with our transformation. Okay, I suggest that we don't orthogonalize this. This is not the classical one, but the orthogonalization here doesn't do anything. The only thing that we have to bother about is the moment we have to do a moment MP. And this is M20 plus M02. And then we also have to do a float MXX, that's M20 minus M02. Yeah, so these two we have to distinguish. Okay? So, and then we have to do collision. Okay, let's start with the easy one. M11 is M11. Wait, let me have a look. So we'll have, okay, the pre-collision version plus omega times. So comes the equilibrium minus the pre-collision version, yeah? So meaning we need to know what is the equilibrium of this thing. What is the equilibrium of M11? Yes, rho. So we have to use rho in the format that we have it here. Yeah, because we already saved this. U. Wait, is this U and V? Yes. X and Y times 3x and y. So that's the equilibrium minus M11. This is how MRT works. So MXX. So what is the equilibrium of that guy? MXX. So these are the hydrodynamic guys. Now let's go to the non-hydrodynamic guys. So because we are not using orthogonality here, okay, so how did we call them in the OMP? Yeah? So this will now be OMP. So how does this work? This is actually I mean, one of them has 1/3. Yeah, so then it would be 2/3 plus this and plus that. And important is that this has to be multiplied with rho. And this would be with MP. So now we are getting ghostly. M to 1 is M to 1. Call this ohms 3, I believe. And now how does this work? How does this work? So they have okay, now we have to, you know, in our head, yeah. So because you're learning from the best Lattice Boltzmann lecture in the world, you should be able just to look at it and give me the answer. Yeah, we have what we've learned is we can factorize this. Yeah, so it's the M20. M20 is 1/3 plus u square, right? And this multiplied by Vx by V. So similar the other way around. So that would now become V, and this would be U. And you know, it's very dangerous. I mean, we can easily make mistakes here. So I'm not sure this is going to work later, but let's give it a try. Okay, now we have one more left, one ghost left. And this can again be factorized. So now we have this here as the M02, and we'll have this here as the M20. So, oops. So, yes, I noticed this. So, okay. Multiplication. Yes, there must be a multiplication. You know, this is a head lock on. Let's always look at the screen. Yeah. Yes. So now we have done the collision. Now what we have to do next is to do the back transform. Now the back transform is not so intuitive, in my opinion. This is why I'm now going to use this computer algebra thing. What we need to do is to solve the set of equations. Okay, we have to build our equations table, and what we are going to do is we build the moments A and B are equal to, say, the moments A, B. And we go from A from 0 to 2 and from B from 0 to 2. Yeah, so we'll generate all the equations. Yeah. Then this becomes a list of lists, and this is not what we want. We want a list, so we'll have to flatten this. We have to flatten this, and then this gives us our equation, a list of equations, and then we have to solve for the populations. So this again we do by a table, and this again we have to flatten. So flatten table, so F, I, and J. And we go from I minus 1 to 1 and J minus 1 to 1 to 1. Are you following what I'm doing? So, okay, so these are the equations. Right, so so here we get, I just noticed one thing. Okay, so here we still have our BGK stuff here together with the push scheme. So I suggest we are going to use this as a kind of a template where we put the back transformation into. But there is one thing I've apparently forgotten, because we have to go back we have to recover our M20. And this we get from, see, we have calculated, we have the sum and the difference of the two. So have MP plus MXX. Yeah, this will give us the right value if we multiply this by 0.5. And the other one, would be that one. Yeah. So then what is happening here? I have a tendency to start with 0. I don't know whether I put it. Let's start with 0, right? So the 0 is this one here, yeah? This has, so unfortunately it's not, I'm not able to copy this now properly. This would be M0, no, okay, no, wait. This is rho x, y. Rho xy, this is the 0 moment, minus M02 minus M20 plus M22, okay? Okay, so this appears to be the back transform of that moment. So M minus minus is the one that is up here. So I see that there is a quarter in front of this, so I'll put a bracket. say this is M11 minus M12 minus M22. Wait, no, that's not correct. Minus M21 minus M21 plus M22. Do you agree? And then we have to multiply this by 0.25. They are in stupid order here. 0 minus is this one here, yeah? It's, you know what, I don't like this order. We'll do it in another way. So this is plus, and minus have a relationship together. Plus is M11 and the other two here with a plus, okay? And yes. So then let's go to plus minus. Let's go to plus minus. Plus minus. Okay, we see the same moments again. Yeah, so I'll take this thing here out and put it to plus minus. So plus minus. It has a minus here. And then it comes with plus 1, 2, and it comes with minus 2, 1. Then we have minus plus. Minus plus is this one. So minus plus again obviously has a minus here. Then it has minus plus, it has a minus here and a plus there. Does this make sense? This does not make sense. What I mean, there's something. We have to watch out. So there is a plus here minus. Oh wait, it appears to make sense. Yeah, okay. So then going back to 0 minus. 0 minus is that one with a half in front of it. Okay. 0, 1. So this is minus M. Wait. Okay, now this is velocity. Minus u. Sorry. Minus v. Yes. Minus v x. Minus v x y. By the way. This is the moment, yeah? Danger. Yeah, so that's minus, wait, this is 0 minus, so 0 minus is here. So then comes plus M02 plus M21 minus M22. Okay? So in my estimation, time 1/2, thank you. You saved us. So in my estimation, this should have a relationship to 0 plus. So I use this as a template. So 0 plus has the first one, okay, this here positive and M and here negative. Okay. So lazy as I am, I will also use this as a template here, knowing that this will not be very, so that we have to change a lot here. So M minus, so this will obviously be U now. By logic, this should be 2, 0 and 1, 2, right? And then we have only one left, and that's step 1. Plus, wait, it is plus 0, okay, plus 0. So plus, this is this one. So by logic, it should have here plus and here. Wait, plus, and it should have here minus. And then plus here. It has different order, oh my God. So, but that should be by logic, it should be like this. You agree? Okay, so then hopefully we are done with this. Now we introduced a new function in here. So what we have to do is, why is this underlined? So, okay, we have to watch out whether I have, why is this underlined? So save. So I still have this bash compile. You know, when we are recording stuff, then this takes an amazing amount of time. Okay, well, I don't know. Lecture 6 plots. Is this what we used? No. Or the run simple, was this what we used? Okay. Okay, first of all, let's just see. Okay, now we see the BGK running, right? Okay, we have with delay bounce back stuff. So since we did not change a lot, we should be able to just write MRT here, but now we have to specify our relaxation rates right here. So as I said, let's do it the simple way and putting them to 1, all of them. So I'll interrupt this. I try to interrupt it. What are we going to do when it does not run now? Okay, it's running. I don't know whether you observed this, but I have the impression that previously there was some oscillations here. Little oscillations here that I don't see now. Yeah, so usually because we use this damping, I mean we can try out the following. If we, I mean, no. The day is done anyway, yeah. So see, what did I tell you? So okay, I told you that if we go further than that, then we often see crashes when we use BGK, right? So let's try this out with 0.9 or 1.99. So I put an LBM dot run steps here, and I will comment the other line. And let's see what this does. Okay, yeah, there is some oscillations here. Bloom. Okay. Okay, let's see whether the other one does any better. I don't know. Yeah, just try. I would there are oscillations. I mean, my judgment would be that it survived longer. Okay, so it appears that there is something not very well at this one point, but other than that, it seems to behave pretty well, and it also looks like it has a bigger Reynolds number, yeah, as it should have, yeah. But we don't see it very well because we have to use. There is one point where the velocity is very large, apparently. Okay, then I would say that even though there is one oscillating or one point with a high velocity, which I cannot currently explain, there's also some oscillation. I'm not sure that this will survive forever. So in principle, what we could do, but I don't know how to do this, we can fix the scale. This is somehow we can set this here, but I don't remember. So you may see, not very clearly, but you may see that this has more deformation because it has a higher Reynolds number. Okay, I think we tortured it today, right? So I'm going to stop here. Thank you for attending and see you next week.